Welcome to SanfordFlipMath. This is PreCalculus. We are working through the chapter on exponential and logarithmic stuff. We are working through the Demana, Waits, Foley, Kennedy PreCalculus book, so they get proper credit so that I don't get into copyright trouble. And we're actually doing this in class live with second hour. Shout out to second hour and of course Paige, because she's making a big deal out of it. And not Jasmine, though, because she's not here. Okay, so we're going to work into some applications of exponential functions, in other words, some word problems. And to do this, though, we need to lay some background. Okay, and I know background is everybody's favorite thing. So what we're going to do is, if I take $100 and I put it into the bank at an interest rate of 3% interest per year, which is completely fantasy right now. Interest rates are now like at 0.03% or something like that, or 0.00. They're incredibly low. But if I do that and I leave it there for a year, 3% of 100, $3. So 3% of $100 would be $3. So now my account is worth $103 after 1 year. Well, if I leave this in for a second year, the 3% is not percent growth on $100 anymore. It's percent growth on $103. So I'd have to do 3% of 103. Well, okay, so we're going to break out our mad elementary and middle school math here and do something like 0.03 times 103, because 0.03 is 3%, times 103. Okay, so we'll do some crazy typing here. 0.03 times 103, 3.09. Wow, we made a lot more extra interest that year. And so if I add this on, now this is $106.09 after 2 years. And then if I do this again, I can figure it out for after 3 years, do it again after 4 years, etc. And so the question becomes, well, what if I want to know if I was able to leave it in for 20 years, could I figure out how much money is there? If I want to do this for 20 years, I don't want to have to do this repeatedly, over and over and over again. And just multiplying 20 times 3, making that 60%, doesn't account for the fact that I'm earning interest on top of interest on top of interest. Because if you recall, when I did the interest the second time, it wasn't just 3% of 100, it was 3% of wherever it went, 103. So it's a little bit different, and it gets a little more complicated. So let's back up for a second, and let's talk about what really just happened. I took 3% of 100, and then I added it on to 100. Okay, so what I did 3% and added it on to the original amount of money. So when I take 3% and add it on to the original, that's my new total. Really, that new total was 103%. So if I just multiply by 1.03, that's the same thing as 103%. Okay, so in other words, I take my original 100 and I multiply by 1.03 and I get 103. For the second one, if I take $103 and multiply it by 1.03, I'm going to get 106.09. My point in this is I can do the percentage of and add it on in one step if I just think about the fact that after I've gained 3%, it's really 103%. Does that make sense? Okay, so what happens the second year then? Wasn't this really 100, the original money, times 1.03, that was the first year, times 1.03 again, that's the second year? Which, of course, I don't want to write like that. I'd rather write it like that. So going back to the little question I posed, well, after 2 years, it's to the second power. After 3 years, wouldn't we multiply by 1.03 again? After 4 years, wouldn't we do that again? So this time, wouldn't that just be $100 times 1.03 to the 20th? And I don't know what that is, but I can type it in. About 180 bucks. Since it's money, we'll do the typical dollars and cents kind of thing. Okay, so let's talk about what just happened. We did the original amount of money times 1 plus whatever that percent was to the number of years. So the question is, why was it 1 plus? Okay, so the 1 is the original 100%. This is the growth. So the idea, again, just like what we just saw, was 100% plus 3% is 103%, which we then convert to a decimal, 1.03. This is 1 plus whatever that percent was. Okay, so let's make this just a little more mathy looking, because, you know, it's a math class and all. So whatever my new amount is, I don't know why the book chose P, is going to be the amount at time 0 times 1 plus R. R is the rate, not at, rate as a decimal, raised to the T power, and T is time, and it's usually the number of years. Because usually the interest rate is a percent per year. Okay, so if we say 3%, and if a 3% interest rate, it's almost always that percent per year. Okay, so that's the formula. A lot of the books I've used use a different setup for the letters, but it's the same stuff. So you might see me slip into this occasionally. This is like the amount you have at time t or whatever. This P is the principal. And principal means the initial deposit or your starting amount, your initial value. And I guess one thing I need to say about this, the rest of it's the same. Isn't this y equals ab to the x? This is A, my initial amount. This big ugly thing right here is B, the thing I'm constantly or repeatedly multiplying by. And instead of X, it's often T. And it doesn't have to talk about money. This can talk about population. This can talk about bacteria. Bacteria growth is at an exponential rate. Yeah, that's lovely to think about. But it's the same stuff. Anything that's exponential growth or exponential decay can be talked about with this kind of a formula. If it's decay, then it might be minus R because it's going away at a rate of 3% per month or whatever. Okay, so let's look at some quick examples, and we'll go from there. All right, so this is over here. It was actually there the whole time. You probably just didn't notice it there. Okay, so we're going to just look at some quick examples, and okay, so we'll do a little initial value. We'll do we'll do some kind of a rate, and then we're going to build an equation. Okay, so this is just going to be a little shorthand way for us to kind of do a bunch of examples in a hurry. Okay, so let's say my initial value is 1,500, like could be $1,500, and we're growing at a rate. So we're going to grow at a rate of 5.2%. We're going to write a little equation for this. Okay, so a little bit. Okay, so this needs to be made into a decimal. And then what we're going to do is do P equals 1,500, or it could be Y equals if you want, or A equals 1 plus 0.052 to the T, or to the X if you prefer. And most people are going to go ahead and combine those. So that's going to be 1,500, 1.052 to the T. Okay, so the 1,500 is the P at time 0. It is the population or the amount or the whatever. Okay, let's do the same thing only backwards. Okay, we're not going to do the problem backwards, but instead of growth, we're going to have decay. Okay, so let's say we have 1 million people, like in the city of Detroit-ish, and let's say we're losing people at a rate of 5%. Okay, so it would say losing 5% every year or decaying by 5%. So now the population is going to be given by what? Okay, so the initial value is 1 million. And this is going to be, because it's a decay, it's minus 5%, so minus 0.05, and again to the T or to the X. So P equals 0.95 to the T. Now, knowing what you know about a base, if a base is less than 1, this is really what kind of a situation? This is decay, so that's good. That's supposed to be, right? Because we're losing people. Okay, people are leaving. They're moving from Detroit to Southfield and to where, I don't know, whatever. All right, so let's really go backwards. Okay, so what I want to know is what was the initial value and what is the rate of growth as a percent. Okay, so if I'm taking this apart, remember this is P0 and 1 plus R to the T. Here's my initial value. And then I need to think about this like 1 plus. Well, this is 1 plus 0.011. So that really is 1.1%. And it's growth, so, I mean, if I was going to follow what I've been doing, then that'd be a plus. It's growth. Okay? All right, one more of these, and then I think we got a pretty good idea of this, but we do have a little tiny bit more to do. Let's do P equals 25 times 0.995 to the T. You'll love that. And by love that, I mean you won't like that at all. I think it's fairly straightforward to say the initial value is 25. The problem now is, what is the percentage rate? Is it growth, decay? What's going on? Okay, so the initial value wasn't hard. This is now the question. This is 1 plus R equals 0.995. That's where it comes from the formula. Now, you can probably notice, obviously, that this was really 1 minus something. The question is, at 1 minus what? Well, this is really, let's not do that. If I subtract it the other way, this is really what did I just do? Oh, I touched the bottom. That'll be fun to watch back. 0.5%. So this is 0.5%, but it is actually a loss of, or you could say negative here, or you could say a loss, or you could say a decay, or whatever, something that implies that it's going down and not going up. Okay, I got one more idea to throw in here, and that's the idea of doubling or tripling or something like that. Okay, so if I am repeatedly doubling, we're going to kind of adjust the formula a little bit. so that we don't have to worry about what's going on. So let's say I have something, let's say the deer population in Southfield is doubling every 4 years. Currently, we have 200, and we want to write an equation for this situation. Okay, so we're assuming if it's doubling every 4 years, that means every 4 years, like 4 years from now, I'll have 400. 4 years after that, I'll have 800. 4 years after that, I'll have 1,600. I'm multiplying by 2. I'm multiplying by 2. I'm multiplying by 2. Probably the easiest way to write this equation is to talk about repeatedly multiplying by 2. Doubling means multiplying by 2. So if I start out at 200, all I'm doing is AB to the x. And I'm repeatedly multiplying by what? 2. Now, there's a little bit of a problem with this. If I write it like that, what does x represent? The way this is written right now, this x represents a 4-year period, a 4-year chunk, a 4-year cycle. So if I wanted to put it, if I wanted to say what's the deer population after 4 years, I really put in x equals what? Because it's one set of 4 years. If I was really going to say after 8 years, I would really put in x equals what? 2, because that's 2 chunks of 4. If it was really after 1 years, I would put in x equals 1/4. Okay, so I'm okay with this written like this, provided you put this little disclaimer on here. Because most of the time, what people are going to do is think x, oh, that must mean the number of years. Well, I need a little, x is the number of 4-year periods. Now, what I would recommend doing is instead write it like this. What should we put as an exponent here? Every time we did, when I did 4 years, the exponent was 1. When I did 8 years, the exponent was 2. When I did 1 years, the exponent was 1/4. What am I doing with this? I'm really dividing by 4, right? 4 divided by 4 is 1. 8 divided by 4 is 2. 1 divided by 4 is 1/4. Well, how about instead I just put x over 4 up there? So now x doesn't mean the number of 4-year chunks. Now x can be the number of years. Okay, so if it's been 8 years, 8 divided by 4 is 2. And I know people don't like fractions in the exponent, but sometimes it just does make life a little easier to work with. Because honestly, most people, if they saw this equation, they would just dump 8 in there thinking 8 years. But that's going to double 8 times, and that's a lot more than what it's really supposed to be doing. So again, I think most people, this is a little more user-friendly. The other way works, but you have to have that disclaimer in there. Okay, if you're going to write it this way, you have to say. Okay, all right, one more example exactly like that, only completely different. Okay, let's say we have some kind of a situation where something's dissipating, it's going away. So let's say we start out with 2,500 gallons of some mystery substance. And it is evaporating away or draining away or going away in such a way that it has half is left, not left with a T on the end, just T there. Half is left every 10 hours. Okay, so we start out with 2,500 gallons of whatever this stuff is. 10 hours later, it's 1,250. half of it is gone. Another 10 hours later, it's half of that. Another 10 hours later, it's half of that. I want to write an equation for how much is left. So how much did we start with? What are we constantly multiplying by? And then the issue is, what do we do for an exponent? So if I just do x, this is the number of 10-hour cycles. And as you have probably guessed, I'm going to recommend instead we write and now x is the number of hours. So we build in that dividing by 10. So, at the end of 10 hours, I'm supposed to have half left. At the end of 20 hours, I'm supposed to have 1/2 of a half left. So this exponent has to become 2 somehow, etc. Okay. All right, well, that's going to do it for the video. So thanks for watching. Bye.